Okay, we will start the lecture of linear algebra. Okay, the overview of linear algebra. And we will start with some basic notations and operations of linear algebra. This should be already been done at your undergrad's linear algebra class, but just to refresh your knowledge here. Okay, so basic notation. And the operation. For a vector, usually you will bold the vector so that you can distinguish that is a value or that is a vector. It's an order set of numbers. And you can use this vector, it can be a 1D vector, 2D vector. We will start with the 1D vector. You can use this X with underline here, represent a 1D vector. We will introduce, it can be x1, x2, x3. So this is a column vector, which include x1, 2, 3. And we can also have a 1D. So this is a column vector. You can also have a 1D vector, which is a row vector. You can write as x transpose will be equals to x1, x2, x3. Okay. So the transpose basically transpose this column vector to be a row vector. You can do some operations on the 1D vector as well. Let's start with the simple one, the addition. Let's say the z vector will be equals to x plus y. Okay, then that will be equals to, let's say that they have the same dimension, which is x1, x2, x3. Y will be y1, y2, y3. Then you will have basically the additions between the 1D vector of x and y. So it's x1 plus y1, x2 plus y2, x3 plus y3. So that is the addition part. Or you can say in a simple way, will be zi in the z vector matrices will be equals to xi plus yn, which is exactly here, you write here, but with a simplified representation. You can also do a multiplication for the vector. Multiplication. You can multiply with a vector, like two vector multiply, or you can just multiply with a scalar. Let's try first with a scalar. And that is a simple one. Basically, you just times number there. So we say z equals to alpha, which is the scalar times x. Then for each z in the matrix will be alpha x1, alpha x2, alpha x3. Or you can write as zi equals to alpha xi here. That is multiply with a scalar. You can also do multiply between two vector. So let's say dot product. Or this is also called inner product. That will lead to a value if you do it in the inner product between two 1D vector. So alpha will be equals to x dot y, or you can also write x transpose y. That is equals to x1, x2, x3 times y1, y2, y3. And the final product will be the sum of xi, yi. Okay, that is the inner product. You can also do outer product. Okay, you can also do an outer product. Outer product. Outer product. Okay, and that will lead to a 2D matrices instead of a value. So you can say this A, if that is a 2D matrices, you will put 2 underline there. Will be equals to X times, so this is the outer product, Y, will be equals to X, Y transpose. Then you will get X1, X2, X3 times Y1, Y2, Y3. So the 2D matrices will be X1, Y1, X1, Y2, X1, Y3, X2, Y1, X3, Y1, X2, Y2, X3, Y3, X2, Y3, X3, Y2. So this is a 2D matrices in which your component will be compose this 9 value of the Aij, where this I will be the row index, J will be the column index, where your Aij will be equals to X, I, Y, J. Okay, and that will be a 3 by 3 matrices because you have basically 3 by 1 column, 1 by 3 row. Then in the end, you will get a 2D matrices consult with 3 by 3 component. So this is 2D matrices. For 2D matrices, we can do the similar thing as what we just did for the 1D vector. For 2D matrix, you can also do addition, okay? C will be equals to A plus B, or you can say Cij will be Aij plus Bij, okay? So these are the 2D matrices. They have the same dimension, okay? Then they can do the addition. That Cij will be equals to each component at the same location and sum together. You can also do scalar multiplication, where C will be equals to alpha A, or you can write as Cij equals to alpha times Aij. Okay, very simple. For the matrices multiplication, the C will be equals to A times B. Or you can write as Cij equals to the sum of Aik, Bkj. And when you do the matrices multiplication, you have to make sure the dimension of A and B are compliant to do the multiplication. So for example, if you have the matrices of the dimension of the matrices A will be M times N, okay? Then the row of B has to be start with N, for example, N times P. Then the dimension of the C will be in the end M times P, okay? Just need to check before you do the multiplication. And you can also do a matrices times, like 2D matrices times a 1D vector. So matrices, matrix, vector, multiplication. You will have Y will be equals to A times X, or you can say Yi equals the sum of Aij, Xj, okay? And you can also check the dimension whether they are compiled to each other. So this will be m times n, for example. Then the dimension of x has to be start with m times 1. Then in the end, you will get m times 1 dimension of the y. Okay? And then you can also do some other operations, such as the transpose, which we already talked before, the matrix transpose. So if the C equals to the A transpose, then you can write the Cij will be equals to Aji. That is the transpose. And there are some special matrices which are very important in our later studies. Matrices, because a lot of the special matrices can help us to decrease the complexity of the operations. Or, we will use particular type of the special matrices to solve our numerical solutions. So that is very important. There are some type of the special matrices I will introduce here, but more details you can refer to the printed out note. So for the diagonal matrices, you can refer, for example, I just make a 3 by 3 matrices. So it will be A11, A22, A33. All the other term will be 0 for diagonal matrices, okay? Of course, you can keep writing to ANN, but all the other number will be 0. So this is a 3 by 3 diagonal matrices. There is a particular type of the diagonal matrices, very important, it's called identity matrices. So that is a particular type. How particular? So the identity matrices is just, for the A11, A22, A33, they are all equals to 1. That is called identity matrices. It's one type of the diagonal matrices. Okay, another type is called triangular matrix. There are different types. There are 4 types of the triangular matrices. One is called straightly lower triangular matrix. So in that type, you will have the matrices look like this, 0, 0. So I still use the 3 by 3 matrices as an example. You will have x, x, x. So where the x will represent a number there. That is the strict lower triangular matrices. So only at the lower side of the matrices have number. All the other parts will be 0. There is also a slightly different, it's just called lower triangular matrix. Without that strictly word, then you can write as here. Okay, so that even the diagonal part can have some number. That is the lower triangular matrices. Of course, opposite way will be the straight upper triangular matrix. So instead of the lower has the value, you will have the upper has the value. The number 4 type will be the upper triangular matrix without this strictly word will be x, x, x. So there are some number at the diagonal part as well as the upper part. So there are some special type of the matrices. We will have more later, but just check the notes and refer that in the note and see the other special type of the matrices.